is a conductor VLSI design professional with over 11 years of combined academia and industry experience. He completed his BTech from Vardhaman Engineering College in 2007 and MBA from UIS Commercial Engineering. He to strengthen his expertise in VLSI, he completed the prestigious CDAC VLSI course in Pune. He then transitioned to the semiconductor industry by joining the Blaze company as a graduate engineer. So he decided the technical expertise. He progressed to the position of senior design engineer. He has 60 years of industrial experience in front-end VLSI design with expertise in digital design and semiconductor development. His journey from academia to the semiconductor industry serves as an inspiration to inspiring VLSI design. Now, I welcome Mr. Ramesh Babu Ganadi to give his valuable speech. Welcome, sir.
Ramesh. I have 6 years experience in front-end design team. Before that, I had experience in teaching also 5 years experience in engineering college. So before that, I was from mechanical engineering. So after last grade, I am teaching again. So that's a little bit is from C code to silicon. So implement of all kind of program. The SQL background is also available. So you must know you will not have that. The example of so you will be so how it is working in hardware. So from C code to this hardware. So how many stages are there? So how we are handling this? So let me explain to you. So how software becomes hardware. So everyone using smartphone, TV, okay. So in suppose let me take one example. So in your profile, all of you have YouTube, WhatsApp, everything is there. So what is that? It is software, hardware. You don't know, but you can say that it is some application there. YouTube, Instagram, WhatsApp, these are all applications only. But you want to use so hardware must be there. Without hardware, nothing. So luckily in our lesson, so we need hardware. Okay, with software and application hardware is without hardware. Okay. What value everyone is saying? I think here some professor, assistant professor, associate professor. So they know these basics, but students are also there. So that's why I started from basic itself. So while saying it is okay, these are new. Okay, but I have to start from basic, so that's why I started from. Okay. So you need to follow how from C program to silicon C. Okay. So first we will write the C program. We will compile that. We will combine that. So what every stage we do, I will explain. So the rate of flow I don't care. Okay, this is the rate of flow. Okay, so first we write C program. After that we'll go to compiler. So next processor design, RTM design, silicon chip. So first I will tell basic level. So here we will write C program. So when you guys are microarchitecture 8085 processors and 8086 processors, right? So what are the results? process. Some instructions are there. So registers are there. Suppose move, register. Suppose R1, R2. So R1, R2 are the inputs we are storing as manually in R3. So I have all everything will do in compiler. Okay. So next process, all computing everything will do in process design. So this is VLSI will do in RTL. We convert into that every computing consists everything into RTL. So next we put the silicon chip. So what is silicon chip? What we have in silicon chip? What we have in silicon chip? Billions of transistors. Why we use transistors? Why we are using transistors? Last week we have transistors. On, off, 0, 1. So computer everything. So you understand only zeros and ones only. Okay, C program it will write program. C is equal to A plus B. But silicon chip it won't understand C is equal to A plus B. So it knows only 0 and 1. So once we will write program, so after that we convert into compiler. So in this compiler we have all instructions. Okay. So the instructions after we have to convert into some zeros and ones that will take care of the RTL design. After that only we will process that entire program into silicon chip. If you have any doubts, please comment and ask. So, okay. So in compiler also we have three. Okay. I will tell you one step by step. Okay. One creating information design ability. This was already my creating case. Okay. So this is what today I am presenting. This is step by step complete journey from C to silicon validation. Okay, so first anything, not only for this. So if you are doing work, so what you need some requirement. You guys all need requirement. Suppose customer care, one customer care, he will tell what he need. Okay, so customer his requirements only. You have to note them. So customer point, so you have to note down the requirements. Next, specifications, SQL, compiler, assembly language, main code language, process architecture. Next, RTL design, functional verification, logic synthesis, physical design, tapeout, reactor application, packaging, and silicon validation. Okay, so from C code to silicon chip, these many stages, total 70 stages are there. Okay, so I will go through step by step. Okay, one by one. First, system specification. So everything, whatever. So if you want to win the chip, everything which starts from here itself. So customer will come, he will tell. So I want the support for intake FB16. My frequency should be some 2 gigahertz, 1 gigahertz, something. Okay. So how many comes? Comes means how many operations per second? Tera operations per second will do. So here I took for example for 100 comes. So what is stops? Why this is? Anyone knows? Regarding comes. Okay. One GK, it is performing. The most performance depends on tops only. Suppose let me take one input. 6 down to 0. 6 down to 0. So you always work, you have to process on that 6 down to 0 only. If you take 8 down to 0, it will happen. System what will give? It will give error. Okay, so before the specification itself, it will tell, hey, how many tasks I can work, how many tasks I can work only. Okay, so if you are increasing your tasks, the performance will decrease. If performance decrease, what will happen? Automatically system will hang. Okay, in some cases, you know mobile phones, right? So some mobile phones will work very fastly, some mobile phones very slow, right? So that is depends on the staff only. Performance. Mainly the performance depends. Okay. So these are the specification, how much power we need. Okay, which memory we are using. So what is the interface we are using? Already one session you guys did, right? So protocols. Okay, we need different types of protocol, AXA protocol, ATP protocol, monitoring artics thing completed, right? So which protocol you have to use? That also the specification itself you have to decide. Before writing your program, so you guys have to decide first. So what are the specifications customer is asking? Okay. So how we have to implement? What is the power? What is the area? In which area I have to build the chip? So everything will come first from here itself. This is the specification. So why C program? We are writing C program first itself. So before going to RPM design everything, so first we have to writing our code into C++ algorithm. So why we are using C++? Anyone? Okay. So why we are writing means it is easy to write this program and we can easily understand. Okay, we can run it fastly. Okay. Suppose some multiplier is there, you know. So we have two operands, so we are multiplying. This is the output. Where in seen as way we can check this is the output from C code, right? Very fastly we can check. So what do we do with C++ program? So we are going to see the specification. There is Intel FB8, FB16, in 16. Okay, these are all data types. So based on the data types, we will implement the C code. So we will verify everything in first C code. So we are building some reference outputs we will store. We will store the reference outputs. So after that, we will implement the RPL design. So the RPL design output will compare with this C program. So both some issues, some bugs are there in that RPL. So that's why to implementing easy, everything in C code. So that's why we are writing that in C. We'll verify first in C code. But understanding or what? Worry. Is just no. So that's what I here. Starting in C is easy to write, debug, and validate. And it produces the golden output. So golden output means, so in RTL, we are getting some RTL output. So we will call that is RTL output. So we'll compare everything.
Trial. Trial. Trial.
So here X is the input. We will call generally. So we call this input activations we will call. Okay. So we are multiplying with weights. So what is weights? Suppose you have one image. So what do we do with that image? So we have to increase the brightness. We have to sharp that image. So what we have to do? We have to apply some brightness thing, right? We have to increase some pixels. So how to increase? So you have to multiply with some weights. So that is in conversation. First, After writing this code, manually we calculate and we will write note down the results. So C code, so we calculate numbers. If you calculate then there is no issue in C. Okay, this will take very only. Usually we have 56 by 56 to 56 by 256 image pictures. But to verify manually it is very right. We can see if we 656 means we need so many manipulations, multipliers, additions we need. Okay, so manually also it is very hard to check it. So that's why also we will write C code, some basic we will verify here. So we'll compare with this golden output. That's why we are writing everything in verse C. Okay. So we are writing, we will take the problem, we are writing into C code. So after that we will compile any syntax errors or whatever it is there, we'll run, we'll note down the golden output. That's it. So this compiler, so code is done in C. So next step, what is the next step? So what we have to do? We need to convert our C code to zeros and ones. So before going to zeros and ones, so next step is assembly language. So we have to convert into assembly language. So you have the here it is there. And R1, R2, R3. You guys all know, right? You are seeing in microprocessor, a microcontroller. So R1, R2, R3. These are the registers. These are the registers. So R2, R3, it sets. So we'll store the result into R1. So code instead we wrote in C code, C is equal to A plus B. But here in assembly language, this is not C is equal to A plus B. We are converting into R1, R2, R3. So first we will convert into assembly language. So R2 is assembly language into binary. So I got 20 key points. So it is like the compiler does human readable code into processor friendly instructions. So these are the so I wrote only one instruction. You guys all know how many instructions you have to add, one, give, okay, subtraction, everything. So anything before execution, so this assembly language must convert into binary, zeros and ones. So this is assembly code. So we received from C code. So it converted into assembly language. So after assembly language, this assembler will do convert into machine code. Machine means you already know that CPUs. So what here it will get only zeros and ones. It will convert into zeros and ones. Okay. So these are the instructions. It will store in these registers. Okay. These every information will convert into zeros and ones. But human can't read. So while seeing 100 100, human can't read it. That is what instruction what is we are doing. Okay. Only human. So while seeing beginning with so we're storing back into our register. So everything is there. That's all you can do. System, machine will understand once that the problem. Okay. So that's why we need so everything is intelligent. So machine this okay. So say whatever you said, that's what I told now. So it will convert into 11001. The system will understand, yes, I'm doing addition. Okay, so I have two registers, I have to store in some other register. Okay, machine will understand and will do the process. storage also I prepared. You guys have to know, so that's why I prepared. In next slides it will come. So what memories we have? So when we use that memories, so register also memory, register also memory. So these memory, everything I prepared on slide, I will explain in that slide. Okay. This thing I think everyone knows. So first we have to fix what is the instruction I'm going to perform. Okay. So fix, next decode, next execute. So memory access and write back. So in memory access we have different types of memories. Okay, register memory, L1 cache, L2 cache, L3 cache, and DDR. So primarily DDR we will use. So first we will read the instructions. What are the instructions we have? We will read. So next, so what are the operations I have to perform? That will be the decode. So after that execution will perform all the operations. We will store that in memory access and will write back again to the storage. And you will be very fast. Okay, a little bit slow, you guys need. Okay. So memory hierarchy. So this is memory thing. You have, suppose you have list, you are adding 2 plus 3. Okay, 2 plus 3 means 5. So how many bits you needed? 3 bits you needed. See, this is simple story. So this purpose, you don't need to use caches DDR numbers. So you can use directly registers. Okay. So at the fastest, but size is very small. Okay. If you need only less size, but you have to perform very fast. In that time, you have to use only register. No need to go for remaining memories. Okay. Next, L1 cache. Okay. This one is very fast, but compared to register, little bit slow, but cycle flow little bit increase compared to registers. Next, save L2, L3. This is area. This is very low, slow. Memory is high. Okay. So how we will check these things? So first we will check one address. Okay. So address we will, only one address we will check. So that address we will divide into some parts. So first address we will check. So it is hit or miss on this register. So we already stored some. We will take in previous slide. So we are doing some instructions. We are fetching, decoding, executing. We are writing back. So where we are writing back? So we are writing in memory. We are writing in memory. Already in that memory, some information is there. Already in memory, we wrote some information. So next, when we are calculating, we are executing something. Suppose repeat addresses are coming. Address statement is only X address is coming 10 times. So every time we have to go to memory and it will come back, right? So automatically performance will increase. Automatically performance will decrease. So that's why what we will do. So we will put this address in on top. So it will compare the address is so it is people are if it is that previous data is there, it will take. If it means then again it will go to the memory block, it will pages and again it will write back. Okay. Memory. Okay. Still we are not already into RTL design, so we are in introduction only. Okay. Why CPU is not enough for RTL? So how CPU will work? How CPU will work? Anyone? How CPU will work? Suppose you have 9 multipliers. You have 9 multipliers. So CPU what it will do? It will process sequentially. One by one. Okay. So 9 multipliers, it will take 9 clock cycles. It will take 9 clock cycles. So it's automatically very slow by using CPU. Okay, that's why you go to A. So A what it will do? So 9 multipliers it will do in 1 clock cycle. So that's what I told in starting, we have 100 clocks, right? So we can do that many performances in single clock cycle. Okay. Here, so what is there? Throughput. How many operations we are performing in 1 second? So that is the throughput. Latency. So latency, throughput, both are different. So latency means so to finish any work, how much time it will take. That is latency. So to finish work, how many operations I am doing, that is throughput. Okay, both are different. So limit will perform very highly. So after CPU is very less. So that's when you move to A. These are the difference between CPU and AI accelerator. So CPU will work sequential, AI parallel. Okay, at a time it will perform all nine multipliers, but here one by one. So, but in AI, we will dedicate to that chip only for this purpose only. We are dedicating that. Okay. So here, higher power, lower power, lower throughput performance is very less here. So here performance is very high, higher throughput. So these are the main difference CPU and AI accelerator. I know, but why it is not good to us. So I only tried C. Instead of one multiplication at a time, it executes hundreds or thousand. I took example of 9 multiplier. So we can take hundred and thousands of multipliers we can perform in single clock cycles. Okay. Now the real part came. So that is hardware architecture. So before reading the RTL code, so the architect will give the inputs, but we call it micro architecture. So he will give micro architecture. So what we are expecting, we follow that micro architecture is a RTL code. Okay. So what are inside the hardware architecture? So the flow is input buffer, memory, accumulator, output buffer. So what are inside the input buffer? So we have to perform operations on size of the events. So what he is expecting, what is the data type he needs. So every information, input side, data types, memories, okay, sizes, everything inside this input buffer. Okay, the array, multiplier, accumulate. So performance will go in array, accumulate will store in this some memory. After it, so it will give information about the images. So input is 56 by 56. Our input image is 32 by 32. So what it will do? It will process from 32 by 32 only. So again it will remain. So here 56 by 56 are there. So here 32 by 32 are there. First it will perform 32 by 32. So still we have input side some pixels. Still it and it will show and it will give next image. So it will distribute images based on input buffer. Okay, so input is 56 by 66. So output should be 56 by 56 is not compulsory. Okay. So RTL describe how the hardware will work. RTL describe how to implement it. So how we have to work. So how we have to hardware that will give the changes. So this, what is that? You have to implement that RTL will describe. So this is parallel thing. So I already told. Pipeline. So if anyone interested to come into citizen, so most important topic this is pipeline. How you are doing pipeline. Suppose what block is there, you have to perform in four stages. Okay, one in your specifications, you have addition, multiplication, move instructions, everything. So what this pipeline will do? So I already told we have one unit. We are divided into four parts. So this four units, what it will do? It will one unit it will make move instruction and subtraction. So it will execute. So while parallelly we are doing it, automatically the performance will increase. Okay, so when we will use suppose so when we will do pipeline. So when we do pipeline is so one example here, move instruction is there. So sorry, this is let's take this and some but okay. So we are multiplying R1, R2, and we are storing in R0. So next we are using this R0 register in addition. Okay, again the result is R3. Again R3 we are using in store instruction. Okay, so there is dependent on previous instruction. These type of instructions we got pipeline. Coming to subtraction, so here R6, R7, R8, there is no dependency on the previous registers. So we can use next second pipeline, we can pass that instruction to second pipeline. So second pipeline will do some instruction. So pipeline is no dependency on the previous instructions. Okay, it will be alone. So that time only we will be pipeline. Okay. Like that only. So automatically system knows. So what are the dependencies are there? So it will separate state by state. Automatically it will go. These are not dependent on previous instructions. These are not dependent on previous instructions. So it will split one. So it will go by that one on. Okay. You only write that code. Okay. why pipeline is pipeline is results produced per second even if the latency of a single operation stays the same. Okay. Let me take one example. We have 20 workers, 10 workers we have. So we have to construct one house. Okay. So it will take 10 days. Suppose it will take 10 days. Suppose you have 40%. You have 40%. So automatically what we have, what we will get our house very fast, right? It will automatically days will reduce. Okay. So what we will do? So we have to distribute 10 people will do this one, 10 people electrical, 10 people plumbing work, 10 people this work. Okay. So we have to divide into 5 times. So these people will work. So automatically what will happen? We can reduce the days, we can get fastly. Our output will become very fast. So that is the pipeline. Okay. That's what we do in design also. Pipeline. Okay. Students. What? Okay. As of now, we distributed one. Okay. The main RTL is the data. Okay. Every calculation in what 3 by 3, 1 by 1 matrix multiplication, everything will do in data path. Okay. Our computations will do on this data path. So first, I already told my input buffer will give the what are the informations, size of the matrices, everything. So it will collect that one. So it has to compute, right? That will come from input buffer. So everything will store in that registers. We have input registers and output registers as well. Let's multiply and accumulate and storing the information. We'll send it to output register and will give final output. With that output only, we will match with golden output. We already have a C, so it matches. That way there is no one. So the actual mathematical performance will do on data path. That was single line. Data path means okay. You can data path is the heart of the argument. So here I don't like. So who tells to argument? Okay, that FSF, you guys already know finite state machines. Okay, first you will do this, you have to read something, you have to distribute. So next you have to compute this multiplication or addition, what? Do what? So who takes this FSF finite state machines only will get information. So we will give first we will give input. So next it will read that the what are the it has to perform addition or subtraction whatever it is. So next it will compute that next it will write in memory. This is finite state machine. So we are doing register transfer level. So why RTL means register transfer level. In naming itself, so we are, we are writing something, we are doing something, so we are storing in that register. Okay, so see here RTL is the register, we transfer here. Again, RT is the register, we transfer here. So what we are doing, registers we are transferring and we are calculating and we are making the output finally. Okay, so that's why it's named as register transfer level. RTL design. We are just what we will do in RTL, we just transferring the registers, we are calculating data path will take care of all mathematical calculations. It will store the output. So this is the VLSI. So now we are using Verila and system Verila codes. You already in your labs also you are writing the codes Verila system Verila. Okay. So only one thing I can tell, if you are writing anything, you are going to lab and you are writing some code, don't see the output. Why you are writing that code? I can write only this way or I can implement in other way also you have to think. If you can't start how to implement that thinking, if you are not starting here, you cannot do anything in after repeating class. Okay. So first, if you are using class, call class, some positives, negatives, level class, whatever it is, why you are using? Think, ask your, okay. So if you only thinking result, so I got result sum is equal to plus 3, 5, it is fine, okay, fine, I got the marks, then there is no use. Okay, why you are using, you have to think. So one customer came, he gave me one project. So artificially we coded everything. It is completed. So next, so I know I don't code. So one time we feel so it is everything is perfect. But you need to verify. Okay. So first you have to say how in C language how you compile and run everything. So same thing in vanilla also. So once your code is done, so you have to compile, check the address and the warnings also. So after that you have to verify. So this is verification that we do. So basically in VLSI we have three parts: front end, back end, and physical design. So front end will write the code, back end guys will verify everything. Back end physical design guys will check this and routing and placements. Okay. So how to verify? So how to verify means you don't give anything to verification guys. So what will happen? So result will write the code. Verification line will go to the architect. We already spec is there. We've got specifications will coming from architecture itself. So I'm telling spec. So in spec every information is there. So he has to go through that spec. So he writes all test specs. Okay. So after so RTL and verification combining together only. So we need to verify. So after result, if it matches, then your design is good. Otherwise, you have some bugs in your RTL, you have to change your code. That's why we are verifying. So in verification also we have two levels: template verification and UMP verification. UMP verification means suppose one project we have multiple units. Okay. So unit level testing means you take only X, Y, Z, some units are there, but we have to pick X block. So you have to verify everything. X is that. Okay. Next Y, next Z. Similarly, how many units are there? You have to verify every unit. That is unit level testing we will call. Then final testing. So together we will test cases will come. So we will verify everything in the whole project. That is next level verification. So initially we will do unit level testing. So after that pipeline testing. So specification, both specifications, RTL and test bench we will do. So calculating. So we will check testing passing or failing. So these are the methodologies. So we have different. We can use test bench C code also. So basically, we are saying we follow the universal verification methodology (UVM). So we call UVM. So by using this UVM methodologies, what is that means? Coding is different. That is so C code Verila, everything is same one. Language is different. C is equal to A plus we are writing in C language. But in Verila, right, left side C is equal to some A B. Okay, it will perform operation. So result is same. So the language is different. Similarly, UVM. So This is universal verification here, how functions we are using, how tasks we are using. So what are they? So in functionally what are they? So here, first, sequencer, driver, DUT, monitor, scoreboard. So test means it will give test name, what we are testing. Suppose together project, both project we are testing. So it will give some environment. With one test itself, we can't test everything. Okay, we need so many test cases. So on test case in that way, I think. So sequencer, next it will drive. DUT means design under test. Design under test. So you will instantiate this DUT in our test bench. So it will take all input information. So once DUT will receive that input information, it will run. So it will give the result in scoreboard. We will compare with our RTL output and original. We already have the golden output. So in March scoreboard, it will take it. Scoreboard will compare the golden output and RTL output. So how verification will help to RTL. So you are getting some in your code, you wrote some 10 down to 0, 8. So it is 11 bits. 11 bits. So when you are dumping on the chip, you have to use this array which should be 11 bits. Okay. But you assign some y is equal to 8, 6 down to 0. Okay. So how many bits here we are using? Only 7 bits. So we are not using remaining everything. So it is automatically no use, right? So there is no use of 8, 10 down to 0. So what you need, 6 down to 0 is enough for your project. Okay. So those things also will do. So that will tell about coverage here. So link with link we will tell. So link will give how many so link will tell us. So unused variables. Okay. Suppose you are typing something, you are not so sorry, when taking something you are not driving to any signal. So that will tell us linked. Okay. So some values holds. Some values, let's take values are there. Everything with your test cases, you will publish everything or not. With these test cases, you will publish or not. So who will tell? We don't know. It's covered everything or not with 1 test, 10 tests, 50 tests. Okay. So we tell how much you tested with your functionality. So you know the code that will call as functionality. So how much that functionality it is there, how much will test? 50%, 60%, 70%. Okay. So this is link, CDC and RDC. So link it will check the coding quality. So any unused signals. So with this matching or any mismatches. So multiple drivers. So any matches are there. So link will check the coding quality. Okay. If you guys are interested, I can elaborate more. Okay. If you are not interested, what I will do, okay, I will finish fasting. Like that I will do. Okay. Program. Yes, okay. So I will try. So see, I am using multiplier. So this is what C is equal to H plus. So after this, what we will do? We will convert into assembler language. Okay. So this is C language. Next, this is assembler language. Next, RTL. We have different. So I'm taking this one behavior. Assign C is equal to B. Okay. So after this RTL, so we need to test this. We are giving some inputs A and B. Okay, we get output, so we have to check the results are correct or not. Okay, so what we know with C reference output, we will compare with our RTL output. Okay, I just took one multiplication example. Okay, but our block has so many calculations part. Okay, so now, okay, verification is done. Now verification also done. Okay, next coming to census. Coming to census. In census, this is physical data. Okay, in census, what will happen? Everything will come to flop. If it will check in census, it is resetable or non-resetable block it will check. Okay, if it is resetable block, then it will use DC, will call flip flop. One. These are regular members, so that's like flip flop. So everything it will write into flip flop. So after that, we'll send it to physical Indian guys. What they will do, they will validate and everything and floor planning where they have to put this A and this B. I am telling my real run. So where one block I have to place, another block where I have to place. So everything block where how to route everything. How I have to route everything. So the placement. So after we have some silicon wafers, they will dump into this floor planning everything. They will dump into the silicon wafer. Automatically chip will come. code how tool. So tool tool means hardware. Just a value. If you guys know these things, then continue. Yeah, correct. But tool is like so. For the RTL thing, we have to use one more. But since we have to use one more tool. Okay. Next time, I will explain. Okay. So next is synthesis. So by using RTL, we cannot manufacture directly. So we need some TSMC files. Get logic. It should convert into some logic gates. So everything will do the synthesis only. The whole RTL to logic synthesis conversion we will do on synthesis by using synthesis tool. So first we will give RTL. So by using some standard cell libraries, okay. So first you can set some time constraints. So it is on sometimes we have some hundreds of flip flops. So everything should work on the same clock. So those things will check out that timing constraints. So this tool will convert the whole RTL into the gate level netlist. We will call gate level netlist. So finally, the chip will give the netlist itself. Okay, here we have elaborated netlist, different type of netlist. So finally, we will take synthesis netlist and we will confirm that silicon chip. Okay. So as of now, we not calculated any power. Okay, so we will check that power. How much power each unit it is taking. So why RTL is that? So since we set this, we will get the census netlist. So after that, we will run some cases. Okay, so while while running this experiment, we'll get so power. So we will run the power test. So we'll get the based on we'll run on the gate level netlist. We receive unit wise power. So in specification, they already mentioned some less than 5.5 unit for this project. So it is maximum not we will check it based on gate level netlist itself. Okay. So in physical state, mainly we have four topics: floor planning, placement, clock with release, and loading. So floor planning, so last I told right, we have 10 blocks. So where we have to put every block in which place. Suppose XYZ in order or XYZ in a vertical where we have to place. So that will decide in that floor plan. So CTS clustering synthesis. Okay. So we have hundreds of flip flops, thousands of flip flops. We have to distribute clock in same time. So how we have to implement that? The CTS will only choose that one. So it will take a CTS itself. The synthesis tool it will set every flop to sorry. To every flop it will set the clock to same time. So CTS tool will take time analysis. So we have to check any setups, hold timing violations are there, any timing violations. So in your RTL code, if you are getting any timing violations, So you will check in this static dynamic analysis. Okay. So design to check LV layout versus schematic, IR graph, electromigration, signal integrity. So what is DRC? Design to check. So what we will do in design to check? Twins are there, or two signals are there. So how much distance you have to put signals? How much winding? So that winding distance, suppose it is very longer, one unit to another unit. So what you have to do? So you have to add buffer. So buffers, by using buffer, there is no input to output change. So there is some rules are there in design check. There, some 3 mm, 2 mm are there. So each unit between the units you have to put any buffer. Suppose one unit is here and 3 units are 5 mm. So in design check group, what it is do, it should be 2 mm only. It will have some buffers between the units. Automatically, the tool will add buffers and will give the results. Everything, this static analysis only we will do. So design to check next layout versus schematic. So everything is there. So finally we will get some diagram. We already have a layout level. We already have a diagram. We will check all the same or not. So what we need to implement, we are implementing same or not. We will check here. Okay. So that is we are checking layout versus schematic. So this IR graph and electromigrations for any voltage drops are there. Suppose you are sending some 5 volts to one unit, 10 volts to another unit. Okay, it should not happen. You have to same everything. So all units, you have to send same voltage. So that point we check in IR graph to send coming from electromagnetic integrated and system integrated. So we cannot fabricate it until this kind of everything, all these checks are done after complete. So we will fabricate the chip of silicon. So if everything is done, then we have to take out. So we have in three TSMC, Samsung, and Intel. These are the foundries. Okay. So Taiwan TSMC we will do in India. It is not there as of now. So in Taiwan TSMC foundry is there. Okay. So the chip will be TSMC, Samsung foundry in Korea, South Korea it is there. And Indian foundry in USA are there. Okay, in USA foundry are there foundries, 2, 3 foundries are there. So if you want to last side of okay, this silicon chip in this Taiwan, South Korea, USA, we are doing. In India, somehow it is not there. Now, Tata is trying to implement in India. Yeah, this is what I told you now. Requirements from requirements to final product. Okay. So in VLSI, first student is not for faculty. So we have this many opportunities in VLSI. Okay. Compiler engineering is we are using to compile an error, right? Suppose you wrote some code, you have to compile that thing. Okay, any syntax error or whatever it is there. So then those things in depends upon the company. Okay, in some every company compiler won't be there. In some companies only compiler tools will be there. Only designers will write the code. They will, so they will in AMD also this compiler is there. In India also compiler is there. So they will verify everything by using this compiler tool. This compiling error everything. AMD. No, yes. who is doing good, so they will don't compare. So they have separate company. Yeah. In India, most of the jobs are verification. Okay, so verification is there. So next, some of them not implemented here. So they are trying to fast verification. So they are using EVM, these things on SV, UVM. SV, by using this only, we are verifying. And also here that Coco, so let me, in future maybe it will come. So as of now, not implemented here. In any company here, we are not using. Protocols, AXP protocols, right? So with NOC we can implement, without NOC also we can implement. Okay, so what it will do NOC means so that protocol we have suppose that chip right project here. One company will do different. So AMD will take care of, suppose AMD is strong in one area. So that's what he will do. So he will give that area part only to AMD class. So next in this, he will give say, project. He will give a customer only give a different types. So I will give this one to AMD, this one to Intel. So after everything we have to put together, we do that project. So that time we use NOC. We will tell every company these are the specifications. So we have to follow this protocol. How many clock cycles, how many frequency you are using, they will tell. So that everything will do NOC. So what? So every NOC they will pay. If they will give it to all every Intel everyone. So by seeing that NOC thing only they have to implement the RTL. So in starting itself without NOC, the company will verify. Individual AMD, suppose AMD is working what customer told, he will verify everything without NOC. So once NOC is clean, so sorry, without NOC is clean, then he will put NOC what customer is expecting. He will put the requirements and again he will verify. Chip place, I know. Yeah, thank you. So this is first thing I came to college from industry level. So what I so you guys know about what is happening inside that industry. So that's what I have to tell my game. So now I understand what you guys are expecting. You have to tool explore you guys are expecting. So definitely if possible next time I will try to come with some tool. Okay. Any doubts what you can ask.
Any talk regarding the concept? So tomorrow we have a practical session. So today only orientation concepts that we have done in the first model session at the moment. And tomorrow we will move with the hands-on sections. Okay. And the venue will be changed for hands-on session. That is 5104 for a session. After this, we move on. Dear students, today our session is going to close, and tomorrow you can join the session of practical. Okay, in the morning, the basic fundamentals. After that, we can continue with the practical part. And now you can take a small break after completing your attendance. You can wait for 5 minutes. HOD sir is going to join us.
ఇవి రెండు అయిపోయిన సింథసిస్ ఇది రెండు అవి బయట ఎక్కడ ఉండవు అవి ఇండస్ట్రీస్ లోనే ఉంటాయి వాళ్ళ లైసెన్స్ అది లైసెన్స్ వస్తున్నాయి వాళ్ళు అవన్నీ లైసెన్స్ వస్తున్నాయి వస్తాయి అవి చాలా ఫాస్ట్ ఉంటాయి సో ఓకే సో అప్పుడు మీరు చెక్ చేయొచ్చు ఏదైనా చిన్న సర్క్యూట్ ఏదైనా తీసుకొని ఫుల్ యాడ్ హాఫ్ యాడ్ తీసుకోవచ్చు చూడొచ్చు Any doubts? Okay, thank you. So we have more in Chinese food, we have tradition. Now we're going to install most so that we're going to be minimum tradition. So before we work on this Chinese tools, we require skill. Basic fundamentals required. That means most important is language and sensibility. As we know, if we don't need an experience from scratch. From frankly reason to bad reason, I experience to know I want the input and output sequence and how to do the language and case language and sensitivity language. It's only when I start from scratch and the VLSI industry depends on over the decades. Mostly ASCII design flow and FPGA design. FPGA and ASCII design flow segments. FPGA is reconfigurable. We can do reconfigurable diversity more design. But in case of ASCII, it is not possible to reconfigure because it is already pre-configured, not able to reconnect. But in case of FPGA, we can. Then what is the main importance of these two things? Six months specifically. In these specific cases, most of the people are high level people, and design level are CEOs. They'll sit together and then discuss what we need to do product. The product require few parameters, especially area, power, speed, and one more time to market. These constraints we're going to discuss, and especially operations. What the fix is, then send to the people who are good in HD. That means hardware description language. Everyone knows. In older days, we used to do two kind of hardware description languages. Previously, we used SDL. Still also we are using SDL, but mostly popular Verilog, SDL along with the system Verilog and UVM verification methodologies. Why we switch to VSG Verilog? Few constraints, few designs are very complex. The complex design not able to do fast because we need to meet time to market. Every industry think about we need to reach time to market early. Your product should be fast and should grow market very fast. So that's the reason based upon that point of view, they switch into Verilog. Some more functional verifications required, then they switch into system Verilog and UVM methodologies for do more functionality. After that, they used to do simulation. What is this simulation will do? Very simple way, straightforward. Simulation is given to check the functionality, whether it's working as per the that's very simple. Two things. Single will take aggregate. When the aggregate will work functionality perfectly, when both inputs 1 and outputs 0, remaining condition will be 0. This is the first. The same way in any complex design, based upon the functionality, whether it's working as per the constraints or not. But we'll check by using simulation. In the simulations, the most important files are two files. The first one is Verilog file. Along with that, one more file is also there. That is also Verilog file, but it is a test page. That is a test page. What's the output of this file? It is also available. Here the market is creating a job that is an RTF verification engineers. What skill required here? Hands-on tools, especially tools, and knowledge on Verilog, digital design concepts, and so on. So what kind of tools we are going to use in this FDP and cadence? Using lots for the simulation technique and allows verification executed. These two modes are other to check the design functionality that is working properly. After this, we expect another technique will be CFX. Here, we check the only functionality. We don't know the structure of the design. So when we came to the structure of the design, when we give this Verilog file along with some more input files to synthesis engine. So what are the input files for synthesis? The one we file. Any other? Any other? Constraints. What do you call? Constraints. Not required test bench. Test bench up to here. For synthesis, not required. Log synopsis design constraints files and along with the Verilog. So what is the output of this? In case of FPGA, it is a bitstream file. What do you call? Bitstream file. And in case of ASIC, you get netlist. In case of ASIC, it is next. So whenever I ask you like ASIC and FPGA differences based upon the generated synthesis output file. These are the synthesis output file for ASIC, synthesis output file for FPGA. From here to here, this stage is called front-end design process. This is completely front-end design process. What next? Next will be the PD. That means physical design process. What happened or what are the input files for physical design means? Which file we are going to give? In case of ASIC, we are going to give netlist. What netlist contain actually? Netlist is contain information about the design, hardware design, that or interconnection between the blocks. First page will be the partition. Floor plan. And routing. Then CTS. Then finally GPS. There are so many routes will be there. In depth, there is STA is also there, static timing analysis. And routing is also most important. So best part is will give best floor plan. Best floor plan will give you best routing constraints. If you are not done properly floor plan, it is unable to justify the routing problems. Like what are the problems will come routing? Congestions, very long length delays. There are so many issues during this process. To overcome that, you should be maintain partition perfectly. That means the macros and IPs, the way we should connect, what is the length of those, all those things will be correct. That is called utilization factor. That means how much percentage of chip area will be occupied. Especially the wafer will be looked at. The wafer will be. What is the importance of utilization here? Means this is completely wafer. This one point is called as a die. This is called die. One die. Inside die, there is a core area. Inside die, there is a core area. Here, your design, complete design will be placed. So here you need to be concentrate where exactly each blocks are placed, how they are communicating. Just like how we have floor plan. If it is 2 feet, it is 1 feet, it is comfortable for you, looking ugly. The same way, here also we need to be take care. So this is completely flow of physical design process. These are PD engineers. We could call as a PD engineers. Here the tools for synthesis, we use RC or genus. RC or genus. After generating netlist, we're going to use Innovus. Completely Innovus tools in cadence especially. Few tools are very good in STA, prime time for synopsis. There are so many tools are. Each and every concept there is a specific tools. So this is a generally the flow of ASIC design and FPGA design flows. To work on the tools, we require commands. Why? Because we are using operating systems not GUI based. It is a completely file based system. GUI means it's a graphical user interface. It's a very friendly and easy to access. But in case of file based system, we need require some commands to access the files. So that's the reason we need to hands-on experience on basic commands. I hope most of people knows the basic commands, but anyway, I'll just remember once again. Any doubts here? Shall we move to commands? Have you heard WSL? WSL? Have you heard WSL? No need to install separately Linux and Red Hat kind of systems. For practicing of Linux and such as scripting kind of programming language. Just go to PowerShell. Or to install it. Install process very simple. WSL hyphen install. Just one command, it will install Ubuntu in your Windows base. No need to virtual machine. For after virtual machine, no need to install again Ubuntu image file, not required. No need that much of space. For particular script, shell script, Perl script, you can use WSL Windows and you can practice on this. So I already installed. So how to launch this? Just use the command WSL. So it will enter into the WSL Windows Subsystem Linux. The abbreviation of WSL is Windows Subsystem Linux. So it is now created. See, previously it was completely Windows. Now it's converted into mountain. Linux. It's subsystem in the GUI. Allow with me. Thank you. Now, so what are the commands? Generally, in Windows based, where you are at A drive and we use to mouse, you go to C drive and A drive. But in case of Linux, where you are, which file you are, what was the command? It's completely command based. So need to be used PWD. What's the command? Present working directory. It's completely file based directories and file system will be there. By using this command, what it show you? It will show you where you are. So, Windows, simple. So, how completely Now, to twist them. Maybe your system D drive, maybe system E drive, there are so many drives will be there. So in my system, I'm using D drive. Now I'm switching from C drive to D drive. On my files in D drive. So once you enter, it will change. See here, we will change C drive to D drive. So changing complete directory. Now, how many files are there and what are the files in my D drive? So we will check by using command. What was the command? Here, just using ls -l. ls is -l. Long list of files with permissions. Option L means it will show you permissions. Means here, each and every file having permissions is here. Read, write, executions. That means in group, admin, and others. We find whenever any access server I'll show you that thing. Once you enter this, see here. This is one of the directories is there. If it is A means it's a directory. The directory having read, write, execution. That is directory. Again, read, write, execution. That is a group. Again, read, write, execution. So, in the directory, anyone can access, anyone can execute, anyone can write. That is the given permissions. So if you want to give any permission to a particular directory, you have to use one more command that is change more command. If you use change more command, then access denied. That is also there. We'll see one by one. First, we will check the basic commands. So to clear this completely, use clear command. Clear complete. Now first we check where we are and what are the files in my directory. Now, you need to create your own directory. How to create your own directory? For example, I want to create a directory. The command is ATAL FDP. FDP underscore DC. This is my directory. I want to create it is complete one week. What are the things will go to? So, once enter, where is created the command? How will you ls. Excellent. Use ls. It will show you where it is. It is there. FDP is there. But it is not find. How would I using the simple command ls-l. It will show you FDP is there. Directly. Yes. It is directly. If it is not, it means just icon means just file based. Directly and file. File based means text based and any Python program, any Verilog programs, all comes under file based. That is icon will be that comes under something. But in case of directly, show you easily. Now my directory is created. I want to go ahead into my directory. What do I want? I want to go into my directory. That is very simple. CD space just use that. If we go use that. Just I enter FB. Now this CD is changed to directly into my own directory. Now see the previous it was in drive. Now it was into my own directory. You want to check where you are? Let's use again the command pwd. The command is present working directory. This is your complete data. This is not data. So your directory will be FTP underscore PC. Here you can create a Windows file or TP file or whatever the files required, depend upon the tools. I can see one shell scripting. So the most important concept is the scripting language. So why important scripting language? In especially VLSI. It will do automation to meet time to market. Why? Because manually you can't able to do millions of gates, functionality, all those things. If you write a simple script and run it, it will run automatically. If any bugs comes, again go back to the script and change according to the requirement according to the errors can change. That is also. First, I'll create one empty file text says correct. That is if you want to create Python program, what was the extension dot py. Based upon the particular language, you can create it. There are so many editors are there. Language is also there, GAV is also there, VM editor is also there, and GVM editor is also. So many editors are there. Depending on your requirement. Simple with GVM is a very simple. But MATLAB, the tools will be the tools will be connected. Then only it will be this. But you can access, you can see the what kind of content is there inside the subdomain. Some program I already have. I'll show you that. So I extended from WSL. That's the reason it's not showing. Now I'm again related to WSL. See, how I'm going to watch the commands. What are the commands you use? Same command directly here. Let's go what inside. So I'm using command and see what are the related files. If it is not related to one files, it is not one files. I want to go back to the file. What is the command? It is not related to one files. I want to go back. The command name is cd space dot doc. The command name is cd space dot doc. I want to go back to the DC data. But I was presenting A1 constituencies and 2007. But I want to go back to the PC data. The command is cd space dot doc. If you enter cd space dot doc, I'm moving into my version. There I will check again whether my available data is there or not. So these are the basic Linux commands. It will be helpful to you tomorrow maths and sessions. Thank you so much. Have a great day.
Within we have a small voluntary has come to the conclusion of the today's program. It is time to proceed with the presentation of our resource person. Now I request Professor Rajendra sir to present our resource person, Ramesh Babu sir. Thank you, sir. Dear participants, as per the schedule, tomorrow we are having the sessions. Tomorrow we have as per the schedule, we are having the sessions tomorrow. Tomorrow session is the 9:30 to 12 o'clock. We are having the session. Tomorrow is 2 to 4:30 we are having another session. That is the organized level. Before VLSI, we are having the session. So the two sessions will be conducted at the meeting having here. So then morning we have a session started here at 9. So participant please be at this time. Thank you very much. Thank you very much for and for your